Okay, so hi everyone. My name is Mrudula Gopalkrishna. Thank you for joining. I'm excited to be here. And I'm, like Sagar mentioned, I'm calling in from the other side of the world, uh, also from the past. So it's 8 a.m. on Saturday here, while you guys are in the evening. So just a fun fact there. Okay, so before I get started, I just want Sorry, some technical issues. I feel I probably okay.
Is there any problem, Mrudula?
I think because it was being live streamed for a second, my computer just like yeah, but that's fine. I'm good now.
Yeah.
Okay. So just a little bit about me. So I was born in Mysore and I did all my like education until undergrad in Mysore. Currently, I'm doing my master's degree in Arizona State University, and the program is called Exploration Systems Design with a concentration in instrumentation. I work currently as a research assistant at the Low Frequency Cosmology Lab, and my research area includes 21 centimeter cosmology and radio instrumentation. Today, I'm going to be talking to you about what 21 centimeter cosmology is and what kind of radio telescopes are used to do 21 centimeter cosmology. So basically, we're going to be covering 4 major topics. One is cosmology basics, and we'll go over the universe's history, give you an introduction about what 21 centimeter cosmology is, and end it off with the kind of telescopes used to do 21 centimeter cosmology. So if you guys have any questions, I probably won't be able to monitor the chat window at the moment, but if you can note down the slide name or like the number, we can go back and I can answer questions in the end. Okay. So before we jump right in, I want to make sure all of us are on the same page about some of the terms used. So I'm going, and so for completeness, even if this is repeated, I'm going to go over the basics and define things first. So what is cosmology? So cosmology is studying the universe as a whole. So cosmologists are interested in figuring out how the universe formed, how it evolved, and what is the future of the universe. So we seek answers to questions like what makes up the universe, how did the universe begin, and what caused the universe to be the way it is. We'll touch on these 3 main questions today, but so these are all very broad questions, but each question has for example, about if we take what makes up the universe, we can study about galaxies, dark matter, normal matter, etc. So these are just broad questions that cosmologists are seeking answers to. So now so what makes cosmology possible? So we are talking about how we want to study the universe as a whole. So I want to go over like what even makes cosmology possible. So to do cosmology, we use light as a diagnostic tool. And when I say light, so usually we are used to thinking about light as visible light that allows us to see. But light is actually a spectrum. It consists of things we can see and things we can't see. And here is just an electromagnetic spectrum, which you probably have seen before. But what I want to highlight is visible light, that is the light that allows us to see, makes up a very small part of the spectrum. If you see the highlighted part here, and the way so everything from radio, microwave, infrared ray, even X-rays and gamma rays, all are basically part of light. Like light consists of all these different paths. The thing is, our eyes are sensitive only to certain wavelengths of light, and radio and microwave. So everything that's on the left have bigger wavelengths. If you see each, so this is just trying to show you that radio has, so in one cycle, it has a bigger wavelength. Well, if you see the same microwave, you see more squiggles, basically just trying to show that on the left side you have longer wavelengths, on the right side you have shorter wavelengths. And if you would have studied this in physics, so basically because of the formula V equals F lambda, frequency and wavelength are inversely proportional. So as you have greater wavelengths, you have lower frequencies. So they're inversely proportional to each other. So I work at the low frequency cosmology lab, which means that it falls in this radio spectrum. It's low frequency and longer wavelengths. Okay, just wanted to show you like what we can learn from different wavelengths of light. So here I have a picture of Centaurus A. It's a galaxy in the constellation Centaurus. And this is how we see it in the visible spectrum. So in the visible spectrum, you see that there's a lot of other stars we can see, and there's a lot of dust, like a cloud fading, like dust there. And on the right, you see how you see the same galaxy in radio spectrum. And what I wanted to highlight is in the radio spectrum, in the radio spectrum, you can see through all the dust, while in the visible spectrum, you see all the dust. And here's another picture. This is the same Centaurus A, but in so every time we study an object, we usually make a multi-wavelength image, which means that we observe the galaxy in different wavelengths, like in visible light, in X-ray, infrared, radio, and then you basically combine all of them to get the full information of an object you're studying. So you can study different things using different wavelengths of light. In the visible light, you get to see the dust and everything near it. And in if you want to see, sometimes every galaxy has emission in all the wavelengths of light, and if you were to only observe one wavelength, you'll be missing out on a lot of information about the galaxy. So this is just to give you an overview of how light is used as a diagnostic tool. There are two main properties of light that makes cosmology possible, and one property of light which we are kind of familiar with is the fact that light travels in finite speed. So we all know that the speed of light is given by 3 × 10⁸ meters per second, which is pretty fast. And I want you to note that like the light from our star, the sun, takes 8 minutes to reach us. So every time we observe the sun, we are actually observing it how it was 8 minutes ago. So if the sun were to explode, we wouldn't know, we would not have any clue until 8 minutes after that. So since light takes a travels in a finite speed, everything we do observe, we are looking at the past, basically. Our nearest galaxy, like the Alpha Centauri, takes about like the light from that galaxy takes about 4 light years to reach us. So whenever we are observing that, we are actually seeing how it was 4 years ago. And this is one of the things, we take advantage of this, and to observe the universe in its past, we just look at objects that are further away from us. So this is one of the properties. And the second property that makes cosmology possible is very important, and it takes a bit to wrap your head around it, but the fact that wavelength of light is stretched due to expansion of space. You might have also heard about this as redshift. So I have an infographic here that kind of explains what redshift means. you can think about redshift as, if it's easier, you can think about it in terms of sound as a Doppler effect in sound. Basically, redshift is Doppler effect in light. So just going over what Doppler effect is, when you have an ambulance that is whooshing past you, when it's closer to you, the sound appears to be louder, but when it's going away from you, the sound appears to be lower in intent. Like it's supposed to be like, it's basically the sound, the volume of the sound changes depending on how close it is to us. The same way, light also undergoes this Doppler effect, and in light it's a little different. Whatever is closer to us appears more blue, and whatever is away from us appears red, and that's why it's called redshift. And if you're looking at light that was emitted very long ago, for example, like nearest galaxy, like Proxima Centauri or Alpha Centauri, it appears redder to us. And this is, and when I say redder, I also, so when I say redder, I also mean that the colors in light is because of the difference in wavelength. So when I say redder, it means longer wavelength as well. So if you see over here, the bluer wavelength has, bluer light has shorter wavelength, but because we know that the universe is expanding. So because of the expansion of the universe, the light, the wavelength gets stretched, and that's why we see the color red, or in other words, we see a longer wavelength. Here is just an animation of like how it stretches on an elastic band. That's basically what's happening in the universe as well. Okay, so now we're going to switch tracks. And since I said cosmology is the study of the universe as a whole, we're going to look at the model of our universe that we think is which we have evidence to, and which we think is how the universe evolved. So what you're looking at right now on the screen is a cartoon of how the history of our universe. Basically, this is the cosmological timeline, if you may. And we'll just take a moment because there's a lot happening in this diagram, and I want to go over each part of it. So on the right side here, you see a familiar image of how the universe looks like today. So here you see all the galaxies. We are used to seeing these galaxies. Our galaxy is also a spiral galaxy, which kind of looks like this. So on the right here, we have the present day universe. And on the left, we have how the universe began. So our universe is believed to have started with a big bang. And this was 13.8 billion years ago. So I'm just going to highlight things that are happening. So redshift is what is on the bottom, and on the top you have the age of the universe. Today, like, we believe the universe to be about 13.8 billion years old. So this is where we are now. And Big Bang is how we think the universe began. We have observational evidence as to how this began, which we can go over if you're interested. But basically, what happened is it started out with a bang, and after the Big Bang, everything was like really hot. And when things are really hot, atoms are stable forms of matter, but when things are hot, atoms ionize. So there was no stable matter, everything was ionized, and everything was really, really hot. But as after the bang, the universe basically expanded. And when you have expansion, if anything's really hot, if you increase the surface area, basically you are cooling. Basically, you're undergoing cooling. So that's what happened. after the Big Bang, there was expansion. Because of expansion, there was cooling. And there was a point where the universe expanded enough that everything became stable. And that is what we call the dark age. So I want you to think about this for a second. So we call it the dark age because there was no light. And there was no light because the universe expanded enough to form stable atoms. When there are stable atoms, there is no emission. And because there is no emission of light, we can't see anything. So basically, I also need to highlight that one of the the most elementary atom in the universe is hydrogen. Even today, if you were to observe the elements in the universe, you would see that the universe is filled with hydrogen. So basically, in the dark age, you had a lot of neutral hydrogen. The way we observe the universe is through light. But if we don't have light, we basically have no access to the universe in this phase. So we know a lot about our present day, and we know a lot about how the universe began, because both the times we have light, but there is one phase in the universe where when it became neutral and we have no access to this age yet. And that age is called the dark age. And after the universe was expanding and we had a lot of neutral hydrogen, but something caused it to collapse and make like clumps, and the first stars and galaxies formed. And we know it happened because we have galaxies and stars today. And that phase is called reionization. Basically, it just means that the formation of the first stars and galaxies in the universe ionized the neutral hydrogen. And today, if you were to look at the universe, it's completely ionized. You don't have any, when I say completely ionized, I mean like between galaxies or between objects, if you were to see, the space itself is ionized. So in cosmology, today's open question is to figure out, this is the missing part that we don't know about and we would like to know. There is a way, we have found a way to probe this era, which is what 21 centimeter cosmology is about, and which we'll see how to do that. Before that, I also just wanted to show you this. So if you were to read any astronomy books, you will see a lot of mention of metals when they're talking about stars and galaxies. They'll basically say there's a lot of metallicity in stars or something. So basically, in an astronomer's periodic table, only three elements exist. One is hydrogen, because that is the most simplest atom to be formed, and then you have helium. Hydrogen fused to form helium, and anything beyond hydrogen helium is termed as metals. So this is just to give you an idea of what astronomers mean. Okay, so now we went over the history of the universe, talked about the dark age, and now we are trying to figure out how to look at this dark age. Segue to 21 centimeter cosmology. So to get access to, so like I said, in the dark ages or epoch of reionization, there was no light. There's a lot of neutral hydrogen, but neutral hydrogen undergoes, this is a forbidden transition in the neutral hydrogen. Basically, it's illustrated here, which means that this is like chemistry 101, where if a stage is if spin states are unstable, they basically try to go to their stable states, and when you go from an excited state to a stable state, you have an emission. So basically, neutral hydrogen has a does emit something called 21 like a spin flip transition. It's 21 centimeter refers to the wavelength of the emitted light. But like I told you, because of the expansion of the universe, 21 centimeter at that time would right now be stretched to meters. And if you remember the electromagnetic spectrum, the meter wavelengths actually fall under the radio spectrum. So that's why like radio astronomy and 21 centimeter cosmology is so closely related. There's also an infographic here. So this is the formula we use to back calculate the redshift. So so redshift and time are closely related, and in astronomy, when you're trying to figure out like when light was emitted, you talk about it in terms of redshift. So this is the formula, and like I said, it gets stretched to like megahertz, which is in the radio spectrum. And in 21 centimeter cosmology specifically, since you're interested in the dark ages and epoch of reionization, the kind of questions we ask is, when did the first stars and galaxies form? How different were they? Are they different from what we see today? Like, do they have spiral arms? Do they not have spiral arms? And we also currently don't really know when exactly the first stars were formed and when this, complete ionization finished. Like, when did it start? When did it end? That is, so imagine you have a picture album of the universe. We have its baby pictures and we have its adulthood pictures. We don't know what happened in between, like what led to the formation of these adults we see today. And that's why I'm going to be talking to you about radio telescopes now, since our interested spectrum is in the radio spectrum, like frequencies. So you might be familiar with dish telescopes. These have been featured in movies. If you have watched the movie Contact by Carl Sagan, this Arecibo was featured in that. So right here is, these are single dish telescopes, basically, which means that there's a large dish. So you can, when you think of telescopes, think about them as light buckets, because all you're trying to do is collect more light. So you see that this is a Greenbank telescope. It's in West Virginia, east coast of USA. And this is Arecibo. If you have been following the news, Arecibo like last year went through a damage because of these cables falling apart. But these are famous single dish telescopes. So now, yeah, I want to also go over just problems with the dishes. So single dish telescopes, you can only build, you can only build certain big, there is a limit to how big you can build a single telescope, because after a point, it will collapse on itself. Literally, it will collapse on itself because of the weight. And we also saw that Arecibo also went through these complications. So you can't build really big single dishes, but if you're trying to, but you need to collect more light. And you also need, and resolution of images is also directly related to the diameter of the dishes. So if you want to build a bigger light bucket, you need a bigger diameter, and you can't build single dishes. So one way to go around it is to build an array of dishes. And this is interferometry. We can go over that as well. But just trying to tell you that just a takeaway is we switched from building single dish telescopes to building array of telescopes to get the same, to basically increase the dish. Like, you can keep it the same, but you can increase the diameter, and also the whole manufacturing complexity, everything decreases if you were to use arrays versus a single dish. Some famous dish arrays is the Very Large Array, again featured in the movie Contact, if you watched it. This is GMRT, which you probably are more familiar with. And this is ALMA, it's in Chile. It's the most sensitive like dish interferometer at the moment. Okay, so now I want to go back and stress on like why we need bigger diameter of telescopes. So here is a picture, and it's from a research paper. So I want to take a minute to tell you what's happening in this picture. So the 21 centimeter signal that we are interested in is shown here. And in radio astronomy, when you're trying to talk about the strength of the signal, it is expressed in terms of brightness temperature. So basically, it's expressed in terms of temperature. And here it's showing you that the 21 centimeter signal that we're interested in is the magnitude is 10 millikelvin. And this signal has been emitted from the very first stars and galaxies. So it's been traveling from a very long time. But after like the formation of the very first stars and galaxies, a lot has happened. Like today we have our own galaxies and we have a lot of other galaxies between us. So basically there's a lot of things between the first galaxies and us today. And that is what is being shown here. So galactic foregrounds is just emission from the Milky Way galaxy, the galaxy that we live in, and extragalactic foregrounds are basically other galaxies in the universe. So, and the brightness temperature of these galaxies, these are also emitting light, and these are in terms of kelvins. So just imagine the signal we are trying to detect is in terms of millikelvin, and everything else that is noise is in terms of Kelvin. So basically the 21 centimeter line that we're interested in is about 10 to the power 5 times weaker than the emission from our own galaxy and extragalactic sources. Which is why if we want to detect it, we need to collect a lot of it. Basically, you need to have a very big light bucket to be able to collect them and to be able to detect this very weak signal. So in scientific terms, we call it collective area. You basically need to increase your collecting area, which just means that you're increasing your diameter of the telescope. But I told you that we can't build single dish telescopes that are that big. And I also told you, and building these arrays are cool too, but right now these are not enough. Like the diameter of these arrays are not enough to detect the 21 centimeter signal. And if you were to add more of these arrays, it's going to cost you a lot of money, because each of these dishes, if you can Google each of these dishes with, and some of the pictures will have humans from their tours, and you can see the scale of how big these dishes are. And to like manufacturing those dishes are really expensive, complicated, and you can only build so many of them. So what do we do now? Now that we have reached our physical limitation, now the hardware limitations, we basically turn to software, and we are going to take advantage of faster computers. So when these telescopes were built, we didn't have supercomputers. Like this one is a very new one, so we do have supercomputers, but basically these two, we didn't have supercomputers then, but we do have them now. So how do we use supercomputers? Basically, how do we use the power of software to pick up where the hardware limitations end? So if you see these dish telescopes, they're designed this way because you can basically point at something, say a galaxy, you can point at a galaxy and you can collect light only from that galaxy. By having dishes, you're basically restricting all the noise that is coming from anywhere you're not pointing. And we needed to do this because humans are noisy. We also use the radio spectrum for a lot of things. We're using it for Wi-Fi, we're using it for cellular communication, we use it for TV, like video signals and everything. So we needed these dishes because we wanted to get rid of all the noise that's around it. But since we have supercomputers now, we can take advantage of the fact that we have a lot of computing power. So we basically listen to everything at all times and use computers to filter out the noise. So that's what we are doing now. And how do these 21 centimeter telescopes look like? They look like this. So these I mentioned, so there are a lot of, there are a few other telescopes as well. I mentioned this because these are the telescopes I'm most familiar with. My lab works with data analysis from these telescopes. That's why I'm mentioning it here. So, you can see that the antennas now went from dishes to being these weird shaped things. Like in this one, you can't even see the antennas. So basically they went from dish antennas to dipole antennas. So these are all different kinds of dipole antennas. So so these three instruments are called first generation instruments. Basically, when you're trying to try out a new concept, you call the telescopes that are built to test that out as first generation instruments. And then you learn from your mistakes, build new telescopes. And this is a second generation instrument. This is also having a dish, but it's an array. And on top of this, like the feed is a dipole antenna. So these come in different shapes, but I want you to notice that the common things that are between them. One thing is now you can't steer them like the dish telescopes you were steering. So basically, since you can't steer, you are listening to the entire sky and you're listening to this at all times. Yeah, so, and I also want you to notice that they are basically the number of antennas in each of these arrays is extremely huge. They're larger than any dish arrays that we have right now. And by increasing the number of antennas, you're increasing your collecting area because you're building a bigger light bucket. And and also you're using these dipole antennas. These are much easier to manufacture, and they're all identical as well. So basically you just mass manufacture these antennas and lay them out in arrays, and you get the same collecting area, and you're also you're increasing your sensitivity, and you're basically getting over all the shortcomings of your dish antennas. So these are one kind of 21 centimeter telescopes. I also want to note that there are two ways in which you can detect this 21 centimeter signal that will tell us about the early universe. And that's pictured here. So this is one way in the bottom, and this is the second way in the top. So these telescopes that I showed you right now are trying to measure this signal, and we'll talk about how to measure this bottom signal as well. If you have read the like if you follow news, like astronomy news, you might have heard that very recently in India there was an instrument, a global 27 centimeter instrument that tried to look at the 21 centimeter signal. We'll get to that as well, but I want you to note that, like, when you're with any signal, if when you're trying to detect it, there are two ways you can detect it. One is you can just measure the average signal of the thing. When you're saying, when you measure an average, you don't get details about the signal. Like, you don't get so the top one is actually giving you a very detailed picture of the signal, whereas the bottom one is just giving you an average. How does it look like? So when you're trying to detect an average of the 21 centimeter signal present in the universe, you use global 21 centimeter instruments. And when you're trying to specifically get 21 centimeter from like dark ages or epoch of reionization or later, you use these telescopes that I just talked to you about. So coming to the global 21 centimeter instruments, the two most famous ones are EDGES, which is in Western Australia. EDGES came about with a possible detection. It's still contested, but it did come out with a possible detection a few years ago. And SARAS-3 is an instrument it's an Indian global 21 centimeter instruments that is making news now. Basically, they looked at the same, they tried to validate the signal detection by EDGES, and according to them, that signal doesn't exist. It is because it is due to like instrumentation system, like systematics. We can go over that as well, but I wanted to let you know that there were two ways in which you can detect the signal, and in India, we are also trying to do that. And SARAS-3 is one of the instruments, and it's on a lake. The antenna is in the middle of a lake, and it's in Bangalore. And it's exciting to just read and know that we are also involved in doing this science. So I've been talking at you for 45 minutes, but I wanted to give you a summary of what we talked about so far. So these are the key takeaway points I would like you to take away from this talk. One is that the cosmology study of properties of the universe as a whole, and we don't know a lot about the first stars and galaxies in the universe, and we can probe that using the 21 centimeter spin flip line. And it's really hard to do. Like, it is really hard to do because the signal is so weak, and we have everything else that's between us and the signal. And again, there are two ways to measure this. One is the global, and the second one is using interferometers, like I mentioned. And I'll leave you with an XKCD comic if you're used to seeing this. This is a comic about the reionization, measuring the 21 centimeter signal. That's because, like I told you, the reionization we expect to measure it in the radio spectrum now, but when I say radio spectrum, we have the FM radio in that band. So this is a comic about that. But yeah, I think I've been talking at you for about 45 minutes now, and I would love to take any questions you might have and discuss. So do you want me to go over the questions, Sagar, or like how do you want me to take questions?
So if anyone have any questions, you can raise your hands or put it in chat box or unmute directly.
Hi. So basically, can you once repeat the concept about the spin flip leading to the 21 centimeter line?
Mm-hmm.
Can you once repeat on what exactly happened? Why is the number 21 centimeter so important to us?
Yeah, of course. So okay, so we are interested in the dark ages, right? I'm not sure. Okay, so we're interested in the dark ages, that phase of the universe. And during the dark ages, we had a lot of neutral hydrogen. And neutral hydrogen, and like I said, when you have neutral atoms, you don't have any emission when you can't see during that era. But neutral hydrogen undergoes a spin flip transition, which basically means, and this is a forbidden transition because it's neutral, right? When it's neutral, it's not supposed to go through this spin flip transition. This is like Yeah, so basically it does undergo a spin flip transition. Even though it is forbidden, we have so much hydrogen in the universe that we can detect a signal. And the 21 centimeter like measurement is important because that when it goes from this parallel spin state to anti-parallel spin state, it emits a signal, and that signal's wavelength is 21 centimeters. And yeah, if you were to, and that 21 centimeter corresponds to 1420 megahertz. So if you were to design an antenna and look at the Milky Way galaxy today, you will be able to detect hydrogen at 1420 megahertz. But if you want to detect the same hydrogen that was emitted a long time ago, you will be able to see this in 46 megahertz, which basically means that you'll have a longer wavelength because of the stretched universe. Does that make sense?
Yeah. So I had a follow-up question. So
Yeah.
is this spin flip the reason that led to the end of the Dark Ages and the beginning of the reionization?
So when the first stars and galaxies formed, they ionized the neutral hydrogen that existed, and that caused spin flip. And yes, so to answer your question, that's what we are trying to map.
Okay, so the formation of the first stars is the reason for the spin flip.
Yes.
Okay. Okay. Thank you.
Hello.
Yes.
Well, I have a question. You said that we use dipole antennas instead of dish antennas, but you
Yeah.
also said that we have a disadvantage that we cannot steer them.
Yes.
So how like they are going and how we are going to take the data from 360-degree, because you said we are using supercomputers and we are getting data all the time from all the directions, but we cannot steer them.
Yeah.
So
Okay. So if you I should have probably had that picture, but so when you have an array of antennas, when you have a single antenna, you can so a single dipole antenna, basically you can see the entire you have a omnidirectional pattern, right, where you can detect everything around around it. But whereas when you have arrays, when you add more dipole antennas near it, the beam basically becomes narrower. Does that make sense?
so the beam becomes narrower, you're saying?
Wait, let me I should try. So when I say when I say non-steerable, I mean that each antenna is not steerable, but the array beam is steerable. Like if you have read about phased array antennas, you can basically steer the beam of the entire array, but you can't steer the beam of each single antenna. Does that make more sense?
Yes, now I got it.
Okay.
Hello, can you please explain about 1 plus redshift? Like it was in the timeline of the universe.
Yeah.
So I want to ask, what does 1 raised to plus redshift mean?
Okay. Sorry. Oh, okay. That I think it was a reference to let me check. So I think it was a reference to this formula where we say like 1 plus redshift, but I'm not entirely sure about that. I'm not really sure about this.
Okay, so we have Akanksha Singh. Can you unmute?
Yes, sir. Good evening, ma'am. Ma'am, my question may sound a little off topic, but for example, if the sun just disappeared for like it just disappeared, it just vanished. So will we like see the effects of its gravity, like the Earth will go flying into the space after 8 minutes, or will that be like instantaneous?
So we would be able to observe the light after the explosion only after 8 minutes. Gravity, I think, will be instantaneous.
Mrudula, can I try answering that? Because
Yeah, go on.
so what happens when suddenly sun disappears is there will be a creation of gravitational wave, and that will propagate at the speed of light itself. So by the time light disappears, in the same time, the gravitational wave will bring that information that sun is not present, and then Earth will be like thrown away
So,
tangentially.
sir, you mean like, for example, if the sun just disappeared, so we'll just keep revolving around nothing till 8 minutes, and then we'll see that the sun is not there, so we'll just go flying into the space.
Actually, it is not nothing. Why? Because right now what Earth is doing is Earth is revolving around the curvature of sun, and
Ah, yeah. So the
so
curvature
even
will stay
when sun
there.
disappears, there will be curvature present as it is, right?
Yeah.
So that curvature will change its form in the speed of light. So it takes 8 minutes.
Okay, sir. Yeah, I got it.
Okay.
Thank you, sir.
That's
Thank you,
so
ma'am.
cool.
I have a question as well on Redshift. Actually, you mentioned how space expands.
Yes.
Could you talk a bit more about that?
So do you want to know like how we know this space is expanding?
Yes, and how it influences Redshift as well. I mean, that is quite obvious, but still, it would be better if you reiterate it.
Okay, so the reason, I mean, we know the space is expanding, and the specific evidence that led to, expand, like us knowing that the universe is expanding, is the Hubble picture. If you, the Hubble, basically Hubble took a picture of a piece of sky and looked at it, and there were a lot of galaxies in that one, small. A piece of sky, and if you were to like basically some of them, and if you were to basically look at galaxies around you, it looks like it's moving away from you, and the way we know that it's looking away from us is the light appears, the spectrum from those galaxies appear red shifted. So if anything is moving further away, the light from that appears to be red shifted, and that's how we know that it's moving away. And everywhere you see all the galaxies around us is moving away, which is why we know that the space itself is expanding. And when it comes to redshift, basically the frequency of your radiation maps to redshift. So depending on the frequency of light you observe, you know exactly what redshift it is from. In other words, you know how long ago, or like how far the object is from us and how long ago the light was emitted.
Thank you.
Vivek, you can unmute and ask a question, Vivek.
Yes, actually, my doubt is not that technical. Like, I don't know if it's pertaining to this discussion. You talked about expansion of the universe, right, in the beginning. So
Yes.
I can't help but ask, like, do we have any understanding about what is the expansion into? Like, expansion, when someone says, like, we always imagine it to be into something.
Yeah.
So,
Yeah. So so that question is valid, and that's something like when we first learn about the universe, we all ask that question. So it's totally valid. What I want you to note is that when you ask that question, you are assuming that the universe is like in some sort of a container, but the universe is not in sort of a container, the universe itself is expanding. There is nothing outside the universe. So the space itself is expanding. Does that make sense?
Space itself, there's nothing outside the universe, basically. That's what
No,
you're
there is there is nothing outside the universe. Like the space itself is expanding, which means that like the space between each objects is increasing, but it's not expanding into anything because we don't think there is anything outside the universe. Like it's not in a container, which means like, you know, it's not expanding itself. Like the space itself is expanding.
But ma'am, like the definition you just gave, the anything that is outside of the universe, because universe is expanding, but the anything that cannot interfere with the properties, which cannot interfere with the universal properties, like at the boundary at which the space is expanding. A particle may have to have certain properties through which it will interact with the boundaries and through which the particles of the universe itself. So what if that those particles, they are of such a nature that they do not interact with the expansion, like the universe is expanding, they are not interacting with that particular universe, but they are there. How can we be sure? Because no such observation has been made to by which we can say about it, like with full uncertainty, with full certainty, and that may be the cause of a multiverse or everything, because the universe is expanding. They are all existing in one particular domain, but
About that, I can, as like, at least for now, I can tell you that those are still theories that need to be tested, and observations are the only way where you can test these theories. And like we can't even, like, you know, to just think about, like, we can't even observe the entire universe really, because our, like, we are limited by like our, like, we have an observable universe beyond which we have not yet figured out how to observe. But yeah, this is where particle physics comes in, and I don't know how that works, but
I mean, yeah, it's like it's a hypothesis, but yeah, there could exist certain particles there which are not interacting, because like as like the participants have said earlier, the universe has to be like it is expanding, but there is some space outside, which means that there is free space outside. We are not generating it. It is expanding into
no,
something.
like,
Or how do we know that it is like if there's nothingness out there, or if there's something out there, how can we be sure?
this is a space continuum fabric thing.
I think
Can we just
a
say
good
that
analogy is consider a balloon and put some dots, and when you blow the balloon, the dots will move far away from each other, but still they are in the same universe, right? It is that scenario, like it is the same analogy that's happening.
I think a nice thought here is that if there was space outside the universe, we would call that space the universe. I mean, if there was more space, then it would be part of the continuum which you define as something that is within your reality or within your universe. So for anything to exist outside it is not a concept or a notion that we can theoretically entertain. So it is basically expanding in itself, and it is not intuitive, but it is something that as at least people who really want to go into cosmology or theorists should become, should get in terms with. I think it's not intuitive for sure, but maybe we can share some resources. It takes a while to get a hang of, but yes, there is, I think we can be confident in saying that there is no space outside of space, because then that would be part of the continuum. And maybe a slightly better example than the balloon is like maybe embedded raisins within like a muffin or a cupcake, and then you put it into the microwave and everything expands at once. and suddenly you see that the raisins or nuts are farther apart than they were. But it's because the muffin or the distance between them itself has expanded. The medium in which they exist itself has expanded. So yeah, there is not more cupcake dough. It's just that the dough itself has expanded. So yeah, I guess that's a slightly better analogy. Not accurate still, but maybe slightly better.
But we can say if even there was a space outside, like you would never see that, because in that case it would be too like that. It would need a lot of time to reach us. So, and
That is already the definition of the observable universe horizon, right? We already have a
yeah,
limit out of which we cannot, it is a theoretical limit, because light outside that horizon would require more than the age of the universe to reach us. So we already have a theoretical limit for what we can define as the observable universe. But that doesn't mean that is the boundary of the universe. So there is obviously more space out there. So how would you define space outside of that?
we can define it as a hypothesis which we can like never access, but it may or may not be there.
Yeah, I think some of you with cosmology questions, you're in for a treat next week, because we have a professor coming in, and she works very actively in cosmology. So those of you who have slightly more theoretical or observational questions, please make a note of them on the Discord server. It would be lovely to address it next week.
I just saw a question in the chat asking about neutral hydrogen. If it's still a single atom or a molecule, it is a single atom.
Hello, ma'am. I have one question. Like we are still getting the trace of 21 centimeter neutral hydrogen line, but we say that today the universe is completely ionized.
Yeah. Oh, you're saying, so the light was emitted after, I mean, so when I say the universe is completely ionized, or like when you read about that, they mean that the intergalactic medium is completely ionized. Intergalactic medium is the keyword there, which means that space between galaxies is completely ionized. But in galaxies, you can still find neutral hydrogen. So if you were to take an antenna and just point it at the sky, you will be able to detect the 21 centimeter line at 1420 megahertz from our galaxy. I can take other questions.
Yes, ma'am. I got another question. Like we say that at first there was like the hydrogen was not ionized. So what led to the ionization of hydrogen? Like it cannot happen by all by itself. So
yeah,
there must be
we think the ionization happened because the first star, like because of the first stars and galaxies. So there was a bunch of neutral hydrogen, and because we don't really, because of density, basically we talk about that in terms of density perturbations. So something led to these density, like basically there was uniform density of neutral hydrogen, but because of then we had clumps of these hydrogen form, and they collapsed and formed the first stars and galaxies, and that led to these neutral hydrogen being ionized. And that's what we can see. We can trace how the neutral hydrogen interacted with these clumps and learn about the universe.
So ma'am, like we can say that as the neutral hydrogen like got clumped up together under pressure, forming the cores, like they got ionized like that.
I would not, yeah, I guess, I mean, I wouldn't say pressure, I would say density, but yeah. So like when you read about like just the early universe, they usually talk in terms of like the changes in density, because that's what led to these clumps and collapse.
Okay, ma'am. Thank you.
You said 21 centimeter is the wavelength of the spin flip transition. So what
Yes.
about vibrational energy transitions? Don't they emit any radiations?
I'm not sure about that. So I mean, we know for a fact that like 21 centimeters is spin flip, and that now we can see in radio. And I forgot, like most of my work is on the radio telescopes that are able to detect this. But there are other transition lines that are used to study different aspects of the like, for example, if you're trying to study star formation in galaxies, you use carbon monoxide molecule emission and stuff like that. But I wouldn't know the chemistry of like vibrational transitions, and I wouldn't be able to tell you because that is not something I've studied.
Saptarshi, you can move and ask a question.
So I had a question regarding the arrangements of the telescopes for the GMRT and the VLA.
Sorry, I couldn't hear you very well.
I had a question regarding the arrangements of the telescopes.
Okay.
So we know that the resolving power goes as proportional to the diameter of the telescope.
Yes. Yeah.
But both the VLA and the GMRT, they take recordings sometimes by putting the telescopes closer together. So what are the advantages and disadvantages of that? Like
so
the VLA has
so you
these
said
rails, and they can take the telescopes closer together to the railway lines.
So you're saying VLA and GMRT use different configurations?
Yes, yes. So,
Yeah.
the GMRT
So
has a lot of telescopes compact in the center also.
yeah.
What are the advantages?
So when in terms of when it's a single dish telescope, your resolution is proportional to, like, basically depends on the diameter of the single dish telescope. But in an interferometer, when you have in an interferometer, basically in an array of antennas, it's the distance between the two antennas that you're using that defines your resolution power. Say for the VLA, if you were to pick one antenna, and the antenna that is the furthest away from it, that defines the resolving power. It's like our eyes, like how two eyes are required to resolve something. Just like that, two antennas are used to resolve on an object, and the distance between the dishes is what defines the resolution. And depending on what you are observing, say if you want to observe if you want to take a high resolution image of one single galaxy, then you will use two antennas that are really far apart, like the furthest part, that's possible. So the distance between the antennas is called a baseline. So your resolution is limited by your baseline in case of an interferometer. But there are some sciences where, there are some science cases where there are multiple galaxies in the patch of the sky. You're not interested in resolving them. You just want to know if they emit some, like a metal or something. So if you want to only observe like a patch of sky, then you don't care much about the resolution. Then you'll only use telescopes that are closer to each other, since you don't worry about the resolution. So that's how you play around with the the configuration. typically in an interferometer, you'll have some antennas that are really close together. This will make sure you get a wide field of view. You can see a larger patch of the sky. Whereas if you have something that's really further apart, then you will be able to resolve something very very well. Does that answer?
Yes, thank you.
Can I ask?
Yeah, sure.
So you, as you told, while observing a particular galaxy, we have to take all the wavelengths of it, right? All the
Yes.
wavelengths. So if we observe the galaxies at the edge of the universe, like in the edge of the observable universe, I mean, like in the cosmic event horizon, we only get radio waves, right? There from
Yeah.
there, right? So we cannot we cannot observe the other parts of the wavelength. So we are missing something, right? Is there a possible way to convert the wavelength to X-rays and visible light, or it's just like we are missing the other wavelengths and just focusing on this radio waves?
Okay, so in a galaxy, say like the galaxy I showed you, we saw that in the radio, like there were jets. So so in a galaxy, there are some processes, like there are different processes that emit different wavelengths of light. And if you are trying to figure out if there is a black hole, then you have to look in the radio waves. So that's why we to see if they're active and things like that. When you're talking about edge of the universe, which basically means that you're trying to observe something that's like in the past. You're able to only observe things in the past, and maybe during that formation, it only emitted, like by the time it reaches us, it will be stretched. So we will not be able to see it in the visible spectrum at all. Like we will only be able to see it in higher wavelengths. Like the most recent telescope, like JWST, it's looking at the universe in infrared because it's trying to look at past. It's trying to look at the very first stars and galaxies. So since they have been, since the light from them has been traveling a very long time, you can only see them today in infrared. Yeah, only things that are close by, only galaxies basically that are close by, and have like, you know, you believe that every galaxy has a black hole. So you will look at it in the like that, you know, radio spectrum to see if there are jets or anything by the black hole. And when you're trying to learn different things about that universe, that's when you about a galaxy, that's when you see at different wavelengths. But at the edge of the universe, you won't be able to see them invisible because the light has just been traveling for such a long time.
Oh, okay. Thank you.
So I have a question that says, how is the universe mapped with the hydrogen line emissions? So the way we do this is, like I said, if you were to take an antenna and measure, if you were to just look at 1420 megahertz, you'll see a signal. That's basically your hydrogen emission. And 1420 megahertz, you'll see a bump in 1420 megahertz if it's emitted today, like if it's emitted at redshift 0. But if it's emitted at redshift 6, where we expect it to be from the first stars and galaxies, you would expect to see a bump in in megahertz frequency range, like 20 to 100 megahertz frequency range. If you were to see a signal there, then you will know that it's from the the 21 centimeter that was emitted a long time ago. So you can map frequency and redshift to the emission that you do see. That's how you map the universe using the 21 centimeter signal.
Ma'am, I have a question. Like we use the radio telescope, so we it's not like, how do I ask you? Like, for example, we need the 21 centimeter signals. So does the telescope filter out all the radiations and only collect 21 centimeter radiations, or does that the computer does all that work?
So it listens to, so typically it listens to everything. For example, okay, an antenna, any antenna like your Wi-Fi antenna or your phone antenna, the difference between Wi-Fi antennas, phone antennas, and these telescope antennas is the fact that in your Wi-Fi and your cell phone antennas are only work only at one frequency. Like you have 2.5 gigahertz or 5 gigahertz Wi-Fi signal, and your antenna works only at that one frequency. Whereas these radio telescopes work at a range of frequencies. So they need to be able to, have a good gain or like response to like 20 to 100 megahertz, say. In this frequency range, it will collect all light. And obviously at 88 megahertz, you will see your FM radio. And you use, after you collect all this data, you will, so what happens is the antenna collects all the wavelengths from 20 to 100 megahertz. And then you'll have filters. I think the other mentor was also supposed to talk about we'll be talking to you about receiving systems. That's when we'll touch this. But as soon as, like, when the antenna receives these signals, they're first, the signals are very weak. So first they're amplified, and then you filter out everything that's that you don't think is your signal. For example, we know that FM signal will be from 88 to 108 megahertz, and we know how much the strength of that signal as well. So we'll filter that out, and we only keep like at a time. Also, you don't you only observe like 10 megahertz bandwidth or something, basically a chunk. You only observe in chunks, and you'll filter out everything that you know for a fact that is not your signal, like Wi-Fi, FM, TV, and whatnot. And that's how, and then you process this data, right? And so filtering and processing, everything happens using computers, because your antenna receives it and it is converted into digital signals. Analog signals are as soon as possible converted to digital signals in radio telescopes, so that you don't lose the signal strength.
And ma'am, one last question. It may sound stupid, but is it possible to build one in a backyard?
Yeah, you can. Like I said, I mean, the first, like, the reason we know the reason we think Big Bang is how our universe, like we know that's how the universe even started, is because of this picture, which I seem to cut. I don't know why. Yeah, it's because of this picture. And this is a picture of the cosmic microwave background. And this was detected sort of in a backyard using a horn antenna.
And ma'am, the WMAP satellite also, the WMAP satellite.
Yes.
WMAP.
Yeah, the difference is that you will not, you will be able to detect signals from our galaxy. But if you want to detect signals that are from faraway galaxies, then you'll need a bigger telescopes. Then your backyard won't be enough.
Okay, ma'am.
So it depends on the size of your telescope.
So, like, technically, it's possible with the right software, and if you get everything.
No, like you will not be able to do it in your backyard, because you will only be able to get to certain, like, diameter. You need a bigger diameter. Technically, like, ideally you would have a telescope as big as the Earth to actually be able to very precisely detect signals from the very first stars and galaxies. Like JWST, which was just very recently put into space, is the size of like a tennis field. That's as big as, like, your light bucket has to be that big. So in your backyard, you only will be able to build a telescope that's strong enough to detect signals from our own galaxy. Outside our galaxies is not something you can build in your backyard.
Okay, ma'am. Thank you, ma'am.
Excuse me, ma'am.
Yeah, go on.
Ma'am, could you please brief us about the sensitivity of the radio telescopes by any chance? Like, from what I have heard from a few scientists during their talks, they have mentioned that in the radio telescopes, usually if the sensitivity is high, the resolution power is low, and vice versa. And yeah, so like that's always been a confusion, and how and why it happens. So like, if possible, could you please brief us about the sensitivity aspect of the radio telescopes as well?
So when you say sensitivity, you mean so when you say sensitivity, you mean that okay, sorry, I'm repeating the same things, but the definition of sensitivity is what is the smallest signal that you can detect using a radio telescope, and that depends on various things. Like it depends on first of all how much light you're collecting. That is dependent on the diameter of the telescope, and second thing is you have to think about your so once you collect the signal, your first job, since it's weak, is to amplify it. And like any signal, like even your phone, like when it's receiving a signal, first thing it does is amplify it. So there is an amplifier on every antenna that receives the signal. So the catch is that this receiver, because of how electronics work, also inject noise into the signal. So your sensitivity is limited by how much noise your instrument, like the noise floor of that instrument. That's the key word. So when you say sensitivity, you mean that what's the smallest signal that will sit on top of the noise floor of your instrument. So, and like I said, that is dependent on the quality of electronics you use in your telescope. It needs to, so the most sensitive telescopes use like the lowest noise amplifiers. That's one area of like, you know, technological advancements that is happening even now. Everyone's trying to build amplifiers that inject the least noise. So low noise, your amplifier needs to be as low as possible, and your telescope diameter has to be as big as possible. So resolution and sensitivity are two different things. So when you're resolving, you're trying to get a sharper image. But when you're talking about sensitivity, you're just trying to detect any signal, like the smallest signal that you can detect in a patch of sky.
Okay, ma'am. But then, okay, so that if you consider this VLF telescope, that's like 1.4 gigahertz.
Yeah.
A very large array. So there are two aspects. The same telescope uses VLF and also NVSS. Then why do we have a stark difference between the resolution? It's like if all the aspects are same, almost same of VLF and NVSS, then why do we have a stark difference in the imagery and sensitivity?
It's not the same, right? Because in an interferometer, the sensitivity, the resolution and like is dependent on not the diameter of a single telescope, but the distance between the two antennas that you're using. Like in an interferometer, your sensitivity is sensitivity and resolution depends on the baseline, not the diameter. So baseline is the distance between two antennas that you're like that are furthest apart. So when you're using a bunch of when you're using an interferometer, very large array is an interferometer, which means that it uses an array of dish telescopes. But the way they're using it is they're making an observation using a pair of antennas at a time. Each pixel in that image is each pixel in that image, right? That's the output of a pair of antennas. So a pair of antennas determine the sensitivity and resolution of that telescope. So if the VLA is, so that's why you can use the same like VLA, but you can use different configurations. In configurations, what they're doing is playing around with the distance between the two antennas. Does that make sense?
Yes, ma'am. But then the operating frequencies are same, right, for both the telescopes? Or are they different? Like operating frequencies for PLAF and NBSS are same, right? Or they are different? Like, I'm just asking out of curiosity.
No, like frequency doesn't matter for resolution and sensitivity. Like at a like those are different concepts.
Okay, all right.
So the same like the two, like this just needs to, like, when you're talking about interferometer, like distance between the antennas set the resolution and the sensitivity. Frequency is set by antenna, like a single antenna actually. Like if you want, so for example, if you want to design a dipole antenna that receives at a certain, like all the array, antenna arrays are identical, right? All the VLA or your the other telescope you were mentioning, all the elements are identical. So that means that each of the antenna is designed to operate at a certain frequency. So frequency is set by the design of a single antenna, but resolution and sensitivity is set by the distance between the furthest of the antennas present in the array.
All right. So you want to say that each antenna is set at a certain frequency?
It's designed to operate
at a certain frequency.
Yes.
Okay.
Not a single one. It's a broadband, right? Like
yeah.
Yeah,
I got the point. Yeah. Okay. Thank you, ma'am.
You're welcome.
Excuse me, ma'am. Okay, you can continue.
Yes. So the hydrogen atoms means the neutral hydrogen atoms flips and goes in the spin flip state, right?
Yeah.
So how frequent is this transition?
It happens. So the chemistry of it, I'm not entirely sure, but what I can tell you is that it is the spin flip transition is called the forbidden transmission, which means that it happens very, very rarely. I don't have a number as to how rarely it happens. It's like the science exists. I just don't know off the top of my head at the moment. But even though it happens rarely, there is so much hydrogen in the universe and has been from the very beginning of the time, because that's the most simplest atom, right? With just one nucleus and one atom, one electron. So like, since there's so much of it and has been there for such a long time, we can detect even though the spin flip is so rare, we can still detect it.
Okay, and when this frequency is released, when it goes from neutral to flip or from flip to neutral?
So okay, so when the idea is that when the first stars and galaxies formed, they emitted light. So these they emitted light, obviously, because when there is any like explosion, there is emission of light, and this light was absorbed by the neutral hydrogen to go in like this excited state, and when it came back to its stable state, that's when you saw the emission.
Okay, thank you, ma'am.
Yes, ma'am. I was asking, like in the one of the slides you just showed that there are two types of telescopes through which we detect the 21 centimeter signals. One was the global one, another one was the spatial fluctuation.
Yeah.
So, ma'am, can you just talk about them and just at the end tell me which one is the better one and which is used?
Okay, that's a good question. That's a really good question. I'm glad you caught that. So, okay, so you can't, first of all, you can't compare the two of them because they're looking at different aspects of the signal. So when you're measuring anything, when you're trying to measure, I'm trying to think about like the best example here. So okay, if you are trying to measure, like, if you're trying to think about like students in a class, or like say students in a school, and you want to and when you're just trying to and somebody asks you what's the strength of the what is the average strength of, like, how many students are present in each class, you will take the average of that and say on an average each class consists of 40 students. But what is happening is that doesn't mean that each class has 40 students. It means that some have, like, majority have 40. Does that make sense?
Yes, ma'am. So this is one
Okay.
for the global one.
So yeah, so global is trying to measure the average 21 centimeter signal in the universe. Like, and like I said, frequency will map to redshift. So you global 21 centimeters like antennas are a single antenna, and it is designed to be broadband between say 20 to 100 megahertz. It is designed to be broadband, and it's a single antenna, and you're only measuring the average properties of the 21 centimeter signal. Whereas in an interferometer, since you have so many baselines, right? Since you have baselines and configurations, you can actually measure the number of students in each class, basically saying how much signal was present at this redshift, how much signal was present in the others. Studying that will, and you also have information as to, for example, in this specific, like today at redshift 0, you know that a lot of galaxies exist. So you will, if you were to map the 21 centimeter in the galaxy, you will be able to tell where hydrogen exists more and where, and because of the redshift, you can also tell which, if the spiral arm is older than the center of the galaxy. Basically study the properties. You're trying to study finer details about the universe using the interferometer, but when you're using a single telescope, you're just averagely calculating how much 21 centimeter signal exists throughout the redshift.
Yes, ma'am, got it.
But these are really good questions. I've enjoyed answering them.
Okay, so does anyone have any other questions? If not, I think we can end the session. Thank you very much, Mrudula. Chitra, if you're here, you can give the vote of thanks. Okay, I think Chitra is not there. Yeah, but still, thank you very much, Mrudula, for joining. And I know it's very early in Arizona now. What's the time now? Can I just know?
It's 9:30 here.
9:30. Okay. So thanks all for joining, and we'll be having another mentor session tomorrow by Himadri.